All right, let's start. Hello, everyone. My name is Carmelo Cascone. I'm an engineer at Open Networking Foundation, where I'm involved in all things P4 when it comes to ONF projects. And I gave this talk also at ONS Europe last year in Amsterdam. And really the goal here is to kind of like provide you a bit of more of a technical details and technical introduction to what P4 and P4Runtime is. We've heard this term a few times during this event, and also give you some examples on how we're using these technologies for the ONF projects. So yes, technical details. I don't think I'll be able to tell you a lot in 30 minutes. And also I think I'm the one standing between you and food and drinks at the reception, so I don't know how much you're excited about this, but anyways, let's start it. So this is the outline. I'll give a brief overview of what P4 and P4Runtime are. I'll talk about the P4-enabled SDN open source stack that is available today, and it's made by things like Stratum, ONOS, and Trellis. And I'll talk a bit about some use cases that we are working on at ONF. So in this talk, I'll talk a lot about data plane pipelines, and how by taking control of these pipelines, we can enable true open networking. So before I start, I want to clarify a bit the terminology. What I mean by pipeline is if you take a switch or a network interface cards, these devices usually have a chip that is devoted to processing packets, forwarding packets. And the way this chip is usually internally designed, it's by using an abstraction that is called a pipeline of match action tables. So the match action tables are, what OpenFlow essentially brought to the masses, even if they were available, since forever. So today we'll talk how to take control of the data plane pipeline and how to enable true open networking by doing this. So the first step to take control of this pipeline is by defining a programming language to define the pipeline. So if you remember OpenFlow brought us the concept of SDN, the separation of control plane and data plane, by providing an API to actually manage these pipelines at runtime by reading and writing state independently of routing protocols running on the box, but using remote logically centralized control planes. But it didn't tell us nothing about what's the specific pipeline in the device. If the device supports all the protocols specified in the OpenFlow specification, if there are other protocols, if some tables are available or not. So P4 comes into help by providing us a way to formally specify this pipeline in terms of which protocol headers are available, which lookup tables are available, the actions we can perform on the packets, and other functions like counters, stateful registers, so forth and so on. It's a programming language that has been designed to describe both fast pipelines, so high-speed forwarding devices like those using ASICs or FPGAs, as well as lower ones, for example, a software switch. And I'll touch on this point many times later. It's good not only for programmable switch, but also for fixed function switch. If you want to motivate P4, it's easy to say programmability is inevitable. Like, I don't know how many of you are developers in this room, but we all are here because probably we understand the benefits of software and the benefits of being able to program our way through this infrastructure. But there is value also in having a formal specification language for a fixed function switch like a traditional one, and I'll explain why in a bit. So this is the workflow you're presented with when using P4. The idea is that you write a P4 program. You compile this P4 program using a compiler that is provided by your switch vendor. And then what this compiler does produces an output that is used to realize this given pipeline on a programmable or fixed function switch. In the case of programmable switch, it will be a binary configuration of the ASIC. In the case of a fixed function pipeline, it will probably be a mapping of the logical tables defined in the P4 programs and the physical ones available in the ASIC. So to give you a little bit more detail on the case of a programmable switch. So P4 is based on this abstract machine model called PISA, which stands for Protocol Independent Switch Architecture, where what you basically have is a programmable parser at the beginning that can be programmed to extract arbitrary headers from a packet, a sequence of generic match action stage units made of basically memory and ALUs. And finally, a programmable deparser and queuing at the end. So the idea of P4 is that you define a logical pipeline, like in this case, a simple standard pipeline implementing layer 2 bridging, IPv4 and IPv6 routing, and ACL. And by using a compiler, you realize this pipeline on your PIS architecture. Now, assuming you decide that for your given network, probably you don't need that much IPv6 routes, and you need a small ACL table, but instead you need a very large IPv4 table. Well, with P4, what you can do is write a P4 program in which you change the program to specify a larger IPv4 table and a smaller IPv6 or ACL table. And by running the compiler, you realize this new pipeline where in this case, you're taking basically double the memory for the IPv4 address table. Now, in these examples, I'm using standard protocols, but clearly P4 is not limited to standard protocols. It's really, if you decide to implement IP version 8 or yet another tunneling protocol, P4 allows you to do that. And if you have a compatible compiler, you can realize that on your programmable switch. This is the case of programmable switches. As I said, there is value also for fixed function chips. And the value of P4 when it comes to fixed function switches is that of using P4 to basically describe not the hardware itself, but the functionality needed at an application level. And then the idea is that you let the switch vendor provide a mapping between this logical pipeline and the physical one. And this, what allows you to do is basically allow portability of your application on an infrastructure that is made of different hardware, different silicon. Like in this example in which we have ASIC 1 and ASIC 2, which are slightly different. But this difference is not exposed to the controller, which instead is able to control a logical view of these two pipelines. I want to touch briefly on a concept that is, I think, very important in answering a number of questions about P4. And this concept is the concept of P4 architectures. So before I described a very simple abstract machine model called the PIS architecture, this is an example of a P4 architecture. There are other examples of architectures where you can compile P4 programs. And by architecture, I mean the availability of components in your pipeline that you can program with P4. So before writing a P4 program, the first thing you need to do is get a hold on an architecture definition from your switch vendor. This architecture definition, what it does, it defines basically which blocks in your pipeline are available, which parser, if there's a deparser, if there's, for example, a packet and queuing and replication engine in the middle. This is what is usually used for QoS or replication for multicast. And availability of match action stages. Once you have this architecture definition file, which defines, again, the blocks and interfaces between the blocks, then you can write a P4 program against it. Example of P4 architectures, probably the most prominent one, is the portable switch architecture. This is a community-developed architecture definition. You can find the specification at this URL. I'll upload the slides soon after the talk. And it basically describes the common capabilities of a network switch, where a network switch is intended as a device with a dozen input and output ports. It provides 6 programmable blocks, and very important, 2 fixed function blocks. And that's because not everything is programmable in P4. And to give you an example, P4 today doesn't offer means to program, for example, the QoS and the packet replication engine of your pipeline. So these functionalities are still fixed functions and not cannot be programmed with P4. Defines also capabilities that go beyond the basic match action table, such as counters, meter, stateful registers, and hash functions. This is an example of architectures. There are other P4 architectures available. One of these is FlexSci, which represents an hybrid programmable fixed function model based on the Sci pipeline. This is an effort that is driven mainly by Mellanox. The idea is that you have a P4 defined pipeline that looks like Sci, or at least that provides fixed function blocks that cannot be modified. It provides standard functionality as defined in Sci. And between these blocks, you have also other programmable blocks where you can inject a bit of programmability. Other architectures are the portable NIC architecture, which is more targeted to network interface cards, which is still work in progress. And then we have proprietary architectures like, for example, the Tofino native architecture if you're using an ASIC like Barefoot Tofino that clearly will expose you all the low-level details of that device. Now, why am I'm stressing so much on the architecture? Because one of the questions I hear the most is, can I use P4 to implement this or that functionality? And if I implement this functionality, will that work on this switch or that other switch from this vendor? Well, the answer, like most engineers say, is like it depends. Because the P4 language per se aims at being flexible enough to describe almost any forwarding behavior that is based on the match action abstraction. But the specific capabilities depend on the architecture. And by capabilities, I mean, for example, the availability of a ternary match versus longest prefix match or exact match, the availability of a component that allows me to do something like ECMP, where I can hash traffic onto multiple ports, the availability of stateful memories that allow me to do some more advanced processing, for example, TCP connection tracking directly on data plane. So these capabilities are usually defined in the architecture file. You won't find any reference to this in the P4 language specification. Then if you ask the question, once I write a P4 program, can I execute this program on a switch from a given vendor? Then the answer is usually yes, if the vendors provide you with a P4 compiler for the specific architecture. This is a bit over-optimistic statement as of today, because then some vendors say, yes, offer support for this architecture, but not for this specific capability. So it's still in early stages, but you get the point, where architectures basically enable portability of P4 programs across different hardware and software targets. This is a summary of the P4 workflow. So once you get once you get a P4, first of all, P4-defined data plane or target or switch, and you get a P4 compiler and architecture model from your vendor, you can write a P4 program, run this program through a compiler. The compiler will generate a target-specific configuration binary that you can use to realize the pipeline on your switch or forwarding device, like a network interface cards. And then you need a control plane to basically populate at runtime all the tables you define in your P4 program. And that's the purpose of P4 Runtime. P4 Runtime is essentially a runtime control API for P4-defined data planes. It's a work that started almost a bit more than 2 years ago, started in 2016. But it was officially, the first version of the specification was officially released in January of this year. It's an open source specification. All the discussion happens on GitHub in the form of issues and pull requests, differently, for example, from the OpenFlow specification that was not public. It was started by Google and Barefoot, again in mid-2016, and then brings contributions from many industry professionals. And a very cool thing is that the specification work in the last 2 years has been based not only on discussions, but also on continuous feedbacks from early implementations and mostly from Google and ONS. For example, we did the first demonstration of P4 Runtime of a running P4 Runtime-based system in 2017. You might be asking, why do we need P4 Runtime? Why can we use existing APIs, say OpenFlow or SCI? Well, the reason is it's simple if you use a table like this. Basically, you can categorize APIs with different characteristics, say, which are important for open networking and SDN, let's say target independence, protocol independence, and pipeline independence. By target independence, I mean the ability of using the same API with different switches from different vendors, and this is definitely a goal of both, for example, OpenFlow and SCI. Then we have protocol independence, which describes the ability of using the same API to control any data plane protocol, standard or custom. And clearly, this is not satisfied by neither OpenFlow and Sign. That's because in OpenFlow, you have the headers and the protocol headers and actions related to that, which are hard-coded in the specification itself. If you look at the specification, you find specific values for, let's say, IPv4 source address, IPv6 destination address. And what if you need to support yet another tunneling protocol? Well, you need to either extend the OpenFlow specification, or the OpenFlow specification actually allows you to provide some extensions, but you will need to implement those extensions about the control plane and data plane. So you cannot really add support for new protocol without recompiling your software stack. For the case of Psi was designed with the goal of offering an abstraction for legacy forwarding pipelines. So there is a goal of supporting only those protocols. Then we have the need for pipeline independence, which is the ability to use the API to control many different pipelines formally specified. When I say many different pipelines, I mean, for example, the ability of having a pipeline that supports only IPv4 routing table and takes all the memory for that, or different table size and shapes. In this case, OpenFlow, in the very end, attempted to do that and accomplished that using something called TTP, and there's no such a thing in Psi. Well, the answer to the question why P4 Runtime is clear, because it's needed to enable this three characteristic. That's what we need. To give you a brief overview of P4 Runtime, it's an API that is based on protobuf, meaning that it provides a very efficient wire format and allows you to automatically generate code to serialize and deserialize messages for many different languages. It uses gRPC as a transport, meaning that we can automatically generate high-performance client-server stubs in many languages. And we get a lot of things for free. For example, the API, differently from OpenFlow, doesn't specify security mechanism, because in this case, by using gRPC, we get for free a pluggable authentication and security features. Also, it offers a very interesting features, which is the support for bidirectional stream channels, meaning that even if it's an RPC mechanism where you have a server-client paradigm, client-server paradigm, in this case, you can still have the server send asynchronous messages to the client. And this is very useful, for example, to support things OpenFlow like packet ins and packet outs. It is P4 program independent, meaning that you can push a new P4 program to reconfigure the pipeline at runtime without recompiling the switch software stack or the control plane software stack. And it's equally good to be used in a scenario like a remote control plane, SDN style remote control plane, or a local control plane. And that's because you have two things. You have the protobuf-based API definition, then you have the gRPC transport. But no one is forcing you to use the gRPC transport. If you decide to implement a switch local control plane, you can find other ways to have your switch local control plane communicate with the P4 Runtime server on the device. Some features at a glance. I'm not going to over detail of those, but just to give you an idea, like OpenFlow, we support clearly read-write of pipeline state. We support batched read and write of the state, things like table entries, action groups, counters, registers. It provides a more robust mastership handling with respect to OpenFlow. This is a problem that we found with production deployment of OpenFlow at ONF, where basically sometimes we have scenarios in which we have mastership flapping, and basically we allow an old master to still write state onto the pipeline, ending up in an erroneous forwarding configuration. So P4 Runtime fixes that problem. It provides very interesting features, which is the ability of running multiple master controller, controlling different portion of the pipeline. So the idea is that differently from the original SDN idea, in which you have one big centralized SDN controller, it's more realistic to think of a scenario in which you have maybe a switch local control plane that, for example, is taking care of handling layer 2 bridging and things like that. and a remote control plane that instead is taking care of, that intelligence that actually requires a global view of the whole network. So you can run multiple controllers on the box and off the box, and that's because P4 Runtime allows you to essentially partition the pipeline and assign different controllers to different partitions. It provides more efficient and flexible packet I/O. By packet I/O, I mean controller packet I/O, so OpenFlow-like packet in and packet out. When I say more flexible, what I mean is the ability to specify additional metadata on the packet ins you send to the controller, and on the packet outs you send on the switch. And this metadata can be defined in P4, so you don't get just, for example, the original ingress port, or you don't just specify the egress port for a packet out, but you can get timestamps, the table that generated the packet in, and some other information that might be interesting to you. It also offers support for so-called digest, which is similar to packet ins. It's essentially a way of batching together a bunch of notifications from the data plane to the control plane, but in this case, without sending the full packet to the control plane, but maybe just a subset of the packet headers. Finally, it's designed around the PSA architecture, so all the PSA constructs are first-class citizen in the API, but it can be easily extended by using the protobuf way of being extensible, which is this any message, if you're familiar with protobuf. Now, how P4 Runtime actually works in the context of control plane and data plane, it's the first thing you need to do is run the P4 compiler. Before, I showed a workflow in which the P4 compiler produces an output that is used to realize a pipeline in your switch. But actually, the open source P4 compiler available today, which is P4C, provides two outputs. First of all, the target-specific binaries, and second, a so-called P4 info file, which essentially represents a schema for the pipeline for runtime control purposes. It's like if you look at the pipeline from the top, and the schema file tells you which tables are available, which fields can be matched on which actions are available. It's based on protobuf, meaning that it can be easily deserialized and consumed by a control plane, auto-generating the necessary code to do that using protobuf. And it's target independent, meaning that you have the same P4 info file independently if you're compiling your P4 program for a software switch, an ASIC, or an FPGA. So in this case, using a P4 compiler, we're getting a P4 info in the binary. The binary will affect only the switch ASIC, while the P4 info will be consumed by the control plane which is the P4 Runtime client, and the P4 Runtime server. And that's because P4 Runtime is a very generic API, and the content of the messages are actually created by looking at this P4 info file. To give you an example, on the left, I have a very simple piece of P4 code, and on the right, I have an example of P4 info file. So in this case, I'm defining a table, a simple IPv4 routing table with longest prefix match capability that matches on the IPv4 destination address and allows you to execute one action called IPv4 forwarding, where this action takes two parameters, the destination address and the port, and that's the action implementation. Actually, there's a bug in this action. If you can find it, we're not rewriting the source address. But that's the beauty of P4. You find a bug, you fix the bug in the P4 program, you recompile it. You don't need to call your switch ASIC vendor. Anyways, you compile this P4 program, and what you get is a P4 info file, where basically what we have is a description of the actions available, the tables available. For each action and table, we get a numeric identifier, and in the case of the actions, a list of parameters available, the name of the parameter, an ID, and a bit width, so the number of bits required for that parameter. The tables available, the ID, the match field, the type of match we can perform, and the bit width of the match fields. So once we share the P4 info file with the control plane and data plane, we can start populating our routing table. So in this case, assuming I want to insert a routing entry that looks like this, where I'm matching on that IP address, and I'm executing the IPv4 forward action with those parameters, This is what a write request P4 runtime message looks like. In this case, I'm using the protobuf text format. This is a nice feature of protobuf, allows you to actually debug your messages by generating a text representation of those. In this case, we have a write request for our device identified with ID 1, and that's because P4 runtime supports this knowledge of a chassis with multiple switching chips, and you can target one of those switching chips. So switch chip with ID 1, the type of update is insert. We can do insert, delete, modify. And this is the content of our table entry. So we are specifying our table using the ID that we found in the P4 info message. We are including a list of match fields using the same ID provided in the P4 info message. And this is the value of, in this case, the match fields as specified here. And then we have the action. Similar to for the table entry, we use the same numeric identifier and identifier for the parameters that we found in the P4 info. So again, basically, P4 runtime is a very generic API, doesn't define any semantic, doesn't define the type of protocol it supports, but the actual content of the P4 runtime messages can be derived from a P4 info file. Next, I want to talk about Stratum. Stratum is essentially a vendor-agnostic implementation of P4 runtime for the switch, so a P4 runtime server. Actually, it doesn't implement just P4 runtime, but implements also other interfaces like GNMI and GNOI. GNMI for config and GNOI for operations. There was a presentation yesterday. If you missed that and would like to know more, I suggest you to look at that presentation. I'll just give you some details here. The goal, Stratum has multiple goals. So the first one is to provide, for sure, an implementation that is vendor agnostic and is production ready, with the goal of essentially minimizing bugs and reducing the time to market for vendors to implement these interfaces like P4 runtime, GNMI, and GNOI. This is the first goal, but also provides a second goal. And since Stratum, one of the main contributors is Google, it's a project that ONF started together with Google. They also contributed a P4 compiler backend for the fixed pipeline model, which is essentially the first P4 compiler that produces a mapping between P4-defined tables and SDK and fixed function switch SDK table APIs. The first target that we plan to support, and the plan at this point is to demonstrate support for this by the end of the year, is Broadcom Tomahawk with SDK LT on top of it. So the idea is that you define a P4 program that clearly abstracts capability that are possible with that fixed function pipeline, and the compiler will produce the necessary mapping to use P4 runtime with that. The third goal is that of providing a conformance test framework along with a repository of tests. And that's because essentially the task of providing a mapping for a given ASIC, even if it's manual or if it's a compiler, it's hard and it's some testing to do. So the idea of Stratum is to provide a whole framework and a series of tests hosted in the same Stratum repository to basically make sure that the vendor-specific pieces of Stratum are implemented as expected. This is a high-level representation of the Stratum architecture. We have the remote or local control plane on the top. We have different components in the middle. These components, some of them are common, so these are hardware agnostic, and some of them have to be provided by either the chip vendor or the platform vendor. And by platform, I mean your box vendor. Then, so the northbound, as we said, is P4 runtime, GNMI, and GNOI. And on the southbound, we usually talk with two things, the switch SDK and the platform API. The switch SDK is will be used to, for example, insert and remove table entries. And the platform API is what we use more for configurations and operations. So for example, configuring ports, getting port speed, polling for port stats, fans, LED, temperature, so forth and so on. If you're interested in seeing more, there is a demo at the ONF booth in which we're demonstrating ONOS running with a small 2x2 list spine topology, running Stratum with multi-vendor white box switches from different vendors. And using the Barefoot Tofino silicon. Now, moving on, I want to go up in the stack. So we talk about essentially P4, so the way we describe the pipeline. P4 Runtime, the protocol that allows runtime control of this P4 defined pipeline. We talked about an implementation of P4 Runtime server for the switch. And now I want to talk about an SDN control plane is available today and supports P4 Runtime, which is ONOS, and some applications on top of it. If you're not familiar with ONOS, it's probably the first project of ONE Lab before becoming ONF, and it's essentially a distributed SDN operating system. It was originally designed to work with OpenFlow and fixed function switches, and at some point we needed to add support for P4 Runtime and this whole idea of programmable data planes and pipeline independence. So in doing this, we set 3 design goals. The first one is we want to allow ONOS users to bring their own P4 programs. We don't want to restrict ONOS users to just a predetermined set of P4 pipelines provided in ONOS. The second is to allow existing applications that are available in ONOS today and perhaps are already used in production to control any P4 pipeline without changing the application itself, essentially providing application portability across different pipelines. Third, because P4 can be used to specify new protocols that were not, perhaps don't exist today, we want to find ways to allow new applications to control custom and P4-defined protocols. So to do that, we came up with this concept of a Pipeconf. A Pipeconf is essentially a way to package together everything that is needed by ONOS to understand, control, and deploy an arbitrary pipeline. It can be distributed as an ONOS app, so you can use the OR ONOS binary format for distribution, and it contains 3 things. It contains the pipeline model, which is a description of the pipeline that is understood by ONOS and is automatically derived from the P4 info file. It contains the target-specific binaries to deploy the pipeline to a device, and this could be, for example, the binary configuration for your Tofino ASIC, the bit stream in case you're controlling an FPGA-based device, or a JSON file in case you're controlling a software switch like BMV2. And third, it contains some pipeline-specific driver behavior. This is probably the most important part. And the idea, as I said at the beginning, is to provide a way to ONOS to understand a given pipeline. Because we have existing application that we want to keep using with this P4 defined pipeline, we use this basically driver mechanism to provide a way to ONOS to map the existing flow programming API to any P4 defined pipeline. So the picture that you get once we implemented this Pipeconf support in ONOS is the following. So we have a Pipeconf store where ONOS takes care of essentially organizing all the Pipeconf that are being registered to the system so far, and then you can pick and choose which Pipeconf you want to associate to a device. ONOS takes care of deploying that pipeline, and then you can have 2 types of applications running on top of ONOS. You can have pipeline-aware application and pipeline-agnostic application. If you're familiar with ONOS, you know that there are different flow programming APIs, such as flow rules and flow objective. The flow rule API is essentially an API that allows you to write and read state from a specific table, assuming that you know your pipeline. The flow objective API instead is a pipeline-agnostic API. It represents a canonical API that can be used for standard functionalities like layer 2, layer 3 routing with ECMP and things like that. So if you're using flow objective, then ONOS will use some translation services that reuse these drivers provided in the Pipeconf to translate those flow objectives into the specific table entries for your pipeline. Instead, if you're using a pipeline-aware application, then it's assumed that your application is aware of your pipeline structure and is using API to write, the flow rule API to write against the specific tables defined in P4. Then today we have 2 drivers, device driver. We have Stratum Tofino and Stratum BMV2. These are Stratum drivers for, with some variation in the way we push the pipeline down for Tofino or BMV2. And as I explained before, this two-driver Stratum is based, again, on these three interfaces, so P4 Runtime, GNMI, and GNOI. Yes? Can you repeat the question? Great question. Yes. Yeah, great question. So very good question. The question is, why do we need an API like the flow objective to abstract the pipeline when we can use P4 to actually abstract the pipeline and don't have ONOS to care about that? I have a slide about this, and the reason it's simple. It's because ONOS was created before P4 was created, so we face this problem of creating application that could be portable on top of different devices. We came up with an abstraction with the flow objective, and we soon realized that this is a Java API, that this is hard to map. It's actually hard to map flow objective onto different pipelines because it's an ambiguous API. It's not well specified. It's actually underspecified. And if you follow the presentation on next generation ONOS, the idea for the next generation of ONOS is to actually drop this layer of abstraction, or at least move it to the P4 level. So leave the duty of providing a mapping to the switch vendors. So in talking about this, I'll provide you an example, one use case of ONOS with P4, which is about creating a silicon-independent fabric. So one of the most prominent ONOS applications is Trellis. Trellis is a set of applications running on top of ONOS designed to provide capability of a leaf-spine fabric that is NFV enabled and can be used. It's used today mostly for access edge applications, and it's in production at a tier 1 operator in the US. It provides a number of features, standard fabric features like bridging VLANs, IPv4, v6, unicast and multicast, DHCP relay, pseudo wires, Q&Q, vRouter, and more. It was originally designed to work with OpenFlow and Broadcom Silicon, and today it supports P4 and P4 Runtime. And I want to tell you how we added support for this. So as I said, it was originally designed to work with Broadcom Silicon, and today we have support for this different chips from Broadcom. On top of ONOS, we have the Trellis applications, and these applications are writing against the Flow Objective API, which is this pipeline agnostic API that I described before, and these flow objectives are then translated to OpenFlow rules by a driver, which is the OF-DPA driver. OF-DPA is an OpenFlow agent created by Broadcom for Broadcom Silicon, which abstracts a logical pipeline that is common across different instances of Broadcom Silicon. So it's a specific instance of a pipeline using OpenFlow as the runtime protocol. How did we add support for P4? Well, first we created a Pipeconf, meaning we wrote a P4 program and a set of drivers, where this driver are then used to translate the flow objectives that are defined by ONOS, by the Trellis applications into P4 Runtime table entries. And by doing this, we essentially added support for more silicon in Trellis without changing the application. So, for example, we have support for Barefoot Tofino, and in the past, we demonstrated support also for devices running Mellanox Spectrum 1. So it's an example of a programmable pipeline and a fixed function pipeline. Fabric.pt is a P4 program that is open source. It's available in ONOS today. And it provides a reference implementation for the pipeline that Trellis, the Trellis set of application expects to control. It is inspired by the Broadcom OF-DPA pipeline, and that's because this is the pipeline we had more experience using when developing Trellis and ONOS. But it's tailored to the Trellis needs, meaning that there's fewer tables and it's easier to control. It's a work in progress. For example, we still miss support for IPv6. The goal here is to bring more heterogeneity in Trellis with P4-capable silicon. And when I say P4-capable silicon, I mean both programmable and fixed function. And that's because Fabric.P4 abstracts a logical, simplified pipeline of very standard features, so layer 2, layer 3, and MPLS. So any switch pipeline that can be mapped with Fabric.P4 can be used in Trellis. It's an open source implementation as part of ONOS, and it's also extensible, meaning that you can add more functionalities to the pipeline, and I'll talk more about this later. To give an idea of how Fabric.P4 was designed, we started from the OpenFlow Flow Objective API, which is a 3-stage logical pipeline. We have a filtering stage. This is where you usually insert rules related to filtering packets based on the input port and the VLAN tag, if there's a VLAN tag. We have a forwarding stage, which represent our FIB and we're for different behaviors. So we insert rules for bridging, routing, MPLS. And then we have the next stage, where we actually provide an implementation for the next identifier provided by the forwarding stage. So this is where we do, where we rewrite headers, we push the VLAN tag if we need to, or the MPLS label. This is where we replicate packets in case we want to implement a multicast or broadcast behavior. Or this is where we do port selection if you want to implement ECMP. So in designing Fabric.P4, clearly we took the easiest path, which is given a pipeline, logical pipeline that we are familiar with, we simply replicated that pipeline in P4. So Fabric.P4, if you look at the P4 program, you will find tables that are organized in a way that really looks like this Flow Objective API. So what's the benefit of this? And this is related to your question, why do we need a Flow Objective API if we can use P4? And that's because P4, the answer is that we no longer need a Flow Objective API. And that's because P4 allows us for what I like to call easier silicon independence. So with the Flow Objective API, we were already able to achieve, with some effort, silicon independence. And when I say with some effort, it's because mapping Flow Objective to new hardware is hard. And we did this experiment in the past. So we originally designed Trellis on top of OF-DPA and Broadcom ASIC. We came up with the driver implementation, which is a complex implementation. We tried to provide other implementation, other mapping implementation for other hardware. And we realized that that's a very hard job. And that's because the API, it's underspecified. It's written in Java. It's written by people that don't have much experience with data plane pipelines, but rather with control plane. Instead, when you use something like P4, which is a formal specification language, it's a programming language, but it's also a formal specification language, you can leave the duty of providing this mapping to the ASIC vendor. They can either use a compiler, like the one that is part of the Stratum project in case of a fixed function pipeline, or a compiler from a programmable ASIC vendor, or it can be also manual mapping. If you're powerful enough, you can ask your ASIC vendor to do the manual wiring of the logical pipeline to those ASIC tables. And because it's a formally specified language, you can build an ecosystem of tools to do conformance testing. You can use verification tools. You can do data plane unit testing against software emulators for the same pipeline and then the hardware. It's definitely much easier to come up with such a mapping when you have something like P4 instead of the Flow Objective API. Was there a question? Mm-hmm. No, the idea in this case is that, so at the beginning, we were the one, so the ONOS developers, we were the one providing the mapping for the different ASICs. And this mapping was very complex. When we moved to the Fabric.P4 model, in which the pipeline is formally defined in a P4 program, the mapping that we implemented in ONOS, it's a very simple one. It's almost one-to-one mapping. But then we leave the duty of providing the actual mapping to the physical pipeline to the ASIC vendor. So in this case, ASIC 1, 2, and 3 will be different vendors. But because P4 is a formally specified language, you can use tools to help you in this mapping process, or you can even build compilers. It's definitely an easier task that of coming up with this mapping than writing it ourselves at the ONOS level. And to give you an example how this also simplified our life in ONOS, on the left, I have the line of codes for the Fabric.pt ONOS driver, and on the right, the one for OF-DPA. For OF-DPA, it's almost 3 times more lines of code. You might be asking, why do you need 2,000 lines of code for a one-to-one mapping between Flow Objective and Fabric.pt? And that's because Java is known to be quite a verbose language. Sorry. Okay, next, I described an open source leaf-spine fabric based on P4. What I'll talk about next is how to extend this fabric to provide more advanced functionality in using what we call VNF offloading. So the idea of VNF offloading is that of taking network functions, usually running in your computing infrastructure or in a middle box, and moving those to your network infrastructure using, for example, a programmable ASIC. The benefits of doing this are many. You have increased performance, and that's because your VNF can be executed at switch length rate in the order of terabits per second instead of gigabits per second. You have reduced latency and jitter, reduced cost, and that's because you have to manage and buy and power less CPU resources, and instead you can use the switches that are already part of your fabric. So one example of this VNF offloading that we did at ONF is mCord. mCord is the mobile profile for the Cord NFV platform and provides access capability. So you have base stations on the left, you have the internet on the right, mCord provides the access functionality and essentially provides an FFV architecture to run the usual mobile core function. So the green blocks represents the control plane VNFs that are standard for a mobile architecture. So we have an MME, HSS, taking care of things like authentication and mobility. Then we have the serving and packet gateway, which in this case is already disaggregated in a control plane and user plane, where the serving and packet gateway user plane, in this case, is that element that is that performs the most traffic processing intensive functions like GTP tunnel termination, filtering and lawful interception, QoS, buffering, or counting packets for billing purposes. So what we did, we started from an architecture like this, and we moved the SP gateway user plane implementation from the servers to the switch using P4. So we wrote a P4 program that performs a simplified version of the serving and packet gateway user plane. So it performs, for example, GDP encapsulation. And we integrated that with the rest of the control plane. To do this, we wrote around 300 lines of P4.16 code, which we integrated with Fabric.pt. I'm not claiming this is a full-fledged serving and packet gateway implementation. There's a long road ahead to reach that point, but it's good enough to demonstrate end-to-end connectivity. There are some important missing features like buffering during handovers, downlink QoS, and which is something that we are saving for future work. But the way we added support for this in Fabric.pt in Trellis is essentially we extended the pipeline. We added a few more tables in the middle. So we added one table in the ingress pipeline to map packets to different GTP sessions for both the downlink and the uplink. And we added a table at the end to actually add the GTP headers to those packets based on the mapping performed before. Once we extended the pipeline, we created a new application on top of ONOS, which is called the SP Gateway U application, which talks directly with the SP Gateway C control plane, which is part of an open source EPC, which was developed by Intel Sprint. And in this case, the SP Gateway C and the SP Gateway U communicate using standard 3GPP CAPS protocol. And this protocol is used to create, modify, delete GTP sessions. And what this application does is simply transform those requests into table entries for the SP Gateway specific tables of the pipeline. We're starting to work on something similar at ONF. We're moving, yes? In this case, we're using Barefoot Tofino. Yes. Only for the lift switch implementing the serving and packet gateway. We demonstrated this at MWC Barcelona last year. We were using, yes, Tofino for the leaf, and then we were using Cavium Expliant and Mellanox Spectrum 1 for the spines. But in this case, the spines were performing standard Fabric functionality. So we started to work on something similar, which is the implementation of a residential service edge, or BNG, in P4. The idea is to enable a fast path similar to MCORD, but in this case for residential access in the CIBA and COMAC exemplar platforms from ONF. The idea is to provide features like PPPA termination, or reverse path filtering, and other features that are common in a BNG. And we are doing this with the help of Deutsche Telekom. Deutsche Telekom already did something very similar in their Access 4.0 project. They came up with a P4-based implementation of the service edge that they contributed to ONF. And what ONF is starting to do now is essentially integrating this implementation with Fabric.pt, so into our Fabric, and then providing an integration with the rest of the control plane for the CIBA and COMAC reference platform. So we are about the end. Few takeaways. I hope I was able to pass you a message whereby taking the control of the data plane pipeline, we can fundamentally enable true open networking. And that's because when we formally define the contract between the data plane and the control plane, then we can easily mix and match silicon from different vendors without changing our control plane stack. I gave you an example how we tried to do this in ONOS by using the Flow Objective API, and we ended up realizing that it was too much of a complex job if you don't use the right way of specifying the pipeline. P4 Runtime, in this sense, is an evolution of OpenFlow, and in this sense, represents one step forward towards the original SDN vision. So control and data plane disaggregation, but now with pipeline independence. And this is very similar to the Lean NFV keynote yesterday, where they were describing about this integration problem in FFV architecture, and that the way they're solving this by simply removing the specific semantics from the API between the different VNFs, but instead coming up with a generic API and leaving up the job of defining schemas for this key value store to someone else. And that's basically the idea of P4 Runtime. Simplify the API to a very generic one to write pipeline state, and use P4 to specify the pipeline. And again, P4 Runtime offers value for both programmable and fixed function chip. Then I want to stress on the fact that P4 is just a programming language. So if you're asking questions like, can I implement this or that in P4, I strongly suggest you to start by reading, instead of the P4 specification, the P4 language specification, start by reading one of the architecture specification. For example, the portable switch architecture. And there you get an idea of what is possible and what is not. And then as a second thing, you might want to call your programmable ASIC vendor and ask if their compiler supports those capabilities as well. And finally, what I presented today is essentially a rich P4-enabled open source stack that is already available and you can use to experiment with your P4 ideas. You have Stratum, which is a P4-enabled switch implementation, which is currently not very open. It's still close to the Stratum project members, but the plan is to have it open sourced soon. We have ONOS, which is an SDN operating system, which has been extended to support P4 and P4 Runtime. And then there is Trellis, which provides a P4 reference pipeline that you can use as a starting point that provides you basic forwarding by using the Trellis ONOS applications. And you can extend to provide more advanced functionality like VNF offloading. And if you want to get started, I suggest you to visit these links. This is a great way to get started hands-on. So there are a number of tutorials around the P4 language. You can learn more about using ONOS with P4 Runtime and also using Trellis with P4 and VNF offloading. And again, I'll upload the slides so you can find the link over there. And this concludes my presentation, and I'm happy to take any question. Vendors? Yeah, so Barefoot Tofino for sure. There is Metronome for network interface cards. I'm aware of another network interface card. It's not a vendor. It's Netcop from Czech Republic. What they do, they provide a P4 compiler for FPGA network interface cards from different vendors. There is the Google FPM compiler for Stratum that can be used with fixed function pipelines like Broadcom Tomahawk. And there must be someone else. There's the NetFPGA project, again, allows you to compile using Xilinx toolchain P4 programs into FPGAs. Mellanox, yes, I don't see anyone from Mellanox in the room. You know, Mellanox has recently got acquired, so I don't know what are the plans if they. I know we worked in the past. We did some demos in which we demonstrated P4 runtime and P4 support on some of the fixed function switches. I don't know what are the plans for the future. Yeah, so you're talking about the ONF demo, Stratum ONF demo. Yeah, so we have P4 enabled switches from different ODM vendors, Delta, Inventec, EdgeCore. They use different flavors of the Barefoot Tofino ASIC, 6.5 terabits, 1.8 terabits per second. They have different SFP form factors, 10, 25 gigabits, QSFPs. More or less ports, more or less fans, more or less CPU, memory. It's truly a great ecosystem in which you buy the hardware that is most suitable for your needs. The P4 program is identical, and that's because they're all using the Barefoot Tofino ASIC. If you write a P4 program that's compatible, if you're using, for example, Broadcom silicon, if you write a P4 program that is compatible with that silicon, in that case, also the P4 program will be the same. Also, the API to do configuration, so port configuration, polling port stats, subscribing for port up and down events, those are the same. Or for example, polling, fans and speed, fan speed values, power, temperature, those are the same, even if the implementation of those is dependent on the platform. So EdgeCore, Inventec, Delta, they provide different APIs. All right, thank you very much.